For generations, the rhythmic clickety-clack of trains was one of the most recognizable sounds of rail travel. That distinctive noise came from steel wheels, repeatedly striking the small gaps left between successive lengths of rail. Those gaps were deliberate engineering features, designed to accommodate the natural expansion and contraction of metal as temperatures rose and fell. Today, on the majority of mainline tracks around the world, that sound has largely disappeared. Modern railways use continuous welded rail, long, seamless ribbons of steel that can stretch for hundreds of meters or even kilometers without a single expansion gap. The shift was not simply a matter of convenience. It was a fundamental redesign of how tracks manage the physical forces of temperature change, wear, and high-speed operation. Traditional jointed track consisted of relatively short rail sections, typically around 12 to 24 meters in many countries, or about 39 feet in the United States, joined end-to-end with fishplates, joint bars, and bolts. Engineers deliberately left a small gap, often a few millimeters wide, between the rail ends. Steel expands when heated and contracts when cooled. The coefficient of linear thermal expansion for rail steel is approximately 11 to 12 times 10 per degree Celsius. A temperature swing of 40–50 degrees C, common in many climates between winter nights and summer days, would cause a 100-meter length of free rail to change length by roughly 50–55 millimeters. Without gaps, the rails would push against one another in hot weather, building enormous compressive forces that could buckle the track sideways or upward into a sun kink. In extreme cold, contraction could pull joints apart or snap the rail under tension. The gaps acted as breathing spaces that absorbed this movement. The system worked, but it came with serious drawbacks. Every joint was a discontinuity. As train wheels crossed the gap, they produced an impact that battered the rail ends, loosened bolts, accelerated wear on fish plates, and transmitted vibration into the sleepers and ballast. Joints required constant maintenance, bolt tightening, lubrication, rail end repairs, and careful monitoring of gap size. The impacts also limited practical speeds, degraded ride quality, increased noise, and raised the risk of defects such as bolt hole cracks or rail end batter that could lead to breaks. In curves, joints could introduce slight kinks. High-speed operation amplified these problems. Above roughly 160 km/h, the repeated impacts became especially damaging and uncomfortable. The solution that emerged was continuous welded rail, often called CWR or ribbon rail. Individual rail lengths are welded together, commonly by flash butt welding in a depot, to produce long panels of 100–300 meters or more, then joined in the field by thermite welding to form continuous strings that may run for several kilometers. The welds are ground smooth so that the running surface is essentially uninterrupted. The classic clickety-clack vanishes. Trains roll more quietly and smoothly, wear on wheels and rails decreases dramatically, and maintenance focused on joints largely disappears. Eliminating the physical gaps does not eliminate thermal expansion. The physics remains the same. Instead of allowing the rail to change length, engineers constrain it so that temperature change produces internal stress rather than movement. Rails are installed and fastened at a carefully chosen neutral or stress-free temperature, typically a value within the expected annual range for the region, often biased somewhat toward the warmer side because compressive buckling is generally more dangerous and harder to detect than tensile fracture. Hydraulic jacks may stretch the rail, or the rail may be heated until its length matches the length it would have at the desired neutral temperature. It is then clipped firmly to the sleepers and the jacks released. From that point, further heating puts the rail into compression, further cooling puts it into tension. The magnitude of the stress is given by the simple relation. Thermal stress equals Young's modulus of steel approximately 210 GPa multiplied by the coefficient of expansion multiplied by the temperature difference from neutral. A 30 degrees C rise above neutral produces roughly 70 MPa of compressive stress, well within the capacity of modern high-strength rail steel, provided the track structure can resist the tendency of the rail to buckle sideways. Modern concrete sleepers, combined with elastic fastenings clips that grip the rail foot with high force, hold the rail tightly against longitudinal and lateral movement. The sleepers themselves sit in a bed of angular ballast stones. The jagged shape of the stones is critical. They interlock under the weight of the track and traffic, generating substantial frictional resistance. When the rail tries to expand and push the sleepers, the ballast mass resists. Properly maintained ballast, well tamped and shouldered, supplies the lateral and longitudinal stiffness needed to keep the track stable under the compressive forces of a hot summer day. Smooth or rounded stones would allow the assembly to shift more easily and invite buckling. The transition to continuous welded rail was gradual. Early experiments appeared in Germany in the 1920s and on American railroads in the 1930s. Wider adoption accelerated after the Second World War as welding technology improved, concrete sleepers became common, and higher train speeds demanded better track. In the United Kingdom, the 1967 Hither Green derailment, caused in part by a broken rail at a joint, helped drive faster replacement of jointed track with welded rail. By the late 20th century, CWR had become standard on main lines in most developed railway systems. It enables the high speeds of modern passenger trains 350 km/h and beyond that would be impractical on jointed track, reduces overall maintenance costs, extends component life, and improves passenger comfort and safety. Continuous welded rail is not entirely free of joints. Special insulated joints are still required for track circuits that detect train occupancy. Switches and crossings introduce discontinuities by nature. At the ends of long bridges or viaducts, where structural movement can be large, specialized expansion joints, sometimes called breathers or adjustment switches, are used. These employ diagonally tapered, overlapping rail ends that slide relative to each other, allowing substantial longitudinal movement while presenting a continuous, gap-free running surface to the wheels. Transitions between CWR and remaining stretches of jointed track, or locations with very tight curve radii where stressing is difficult, may also retain conventional joints. In these cases, the gaps or sliding interfaces are engineered and maintained with the same care once applied to ordinary rail joints. If you enjoyed this deep dive into one of life's ordinary mysteries, make sure you hit that like button, subscribe to Ordinary Why, and turn on notifications so you never miss the next one.